Hello everyone. My name is Doug Creager, and I'm a software engineer on the Interneto team at Google. Our job is to monitor the edge between Google's network and the public internet, looking for performance and reliability problems. And today I'm here to talk to you about packet captures. I hope to convince you of two things. First, that packet captures can tell you useful information about your application, which you can't easily get from other data sources. And second, that you don't need to make any fundamental changes to your monitoring stack to tap into this new data source. So you'll get great new intelligence in a minimally invasive way. What's not to love? So to start with, let's dig into a hypothetical music streaming application. And we're going to keep things nice and simple. The user asks for a song, a particular song, and the application server starts streaming an audio file to our client. Our client receives the file and starts to play it. Very nice. And since the audio file is pretty big, we're going to start playing the song before it fully arrives and continue playing it while the rest of the data comes in. Simple, right? Bring in the investors. We've got a good working app. So we've got an app deployed to production, and for the most part, things are working great. But we start to receive some reports from our customers. They're accessing the application like they're supposed to. They request a song. The file starts streaming back. The client starts to play the song, but then they get pops and drops, and the audio starts to cut out. This is not good. The skips aren't very long, but they're long enough to be annoying. And I think the first important point here is that you can tell that this is not a happy story, since the problem was reported by our customers, and that's not great. We want it to be detected by something automated so that we can mitigate this and fix it before it turns into an actual user-facing customer quality issue. So not only do we need to dig in and figure out what's causing this problem, we want to do so in a way that we can monitor continuously moving forward. Now, based on our understanding of the problem domain, we can make some educated guesses. The skipping tells us that we probably have an issue with throughput, how quickly the data is being sent or received. And in particular, our client is probably not receiving the audio data quickly enough to keep up with the playback. We receive some data, we start playing it, and then we run out of audio to play before the next portion of the streaming connection arrives. Great, so we have a hypothesis. How can we test it? Is there anything we can get from our existing application? Well, we could check the server. We probably got a good set of server logs that we can query. And it doesn't really matter here how or where the logs are stored or how you access them. The key point here is that they tell us that we sent, for instance, about 10 megabytes spread out over about 5 seconds or so. And that gives us an average throughput of around 250 kilobits per second. That's something to keep in mind. We'll probably measure amounts of traffic, amounts of data in bytes, but then we're going to measure rates in bits because, of course, we have to use something different there. So there's going to be a factor of 8 difference in some of these numbers, in case you were trying to do the math there in your head. Okay, so 250 kilobits per second is our average throughput, and we know that we encoded the audio at kind of around 128 kilobits per second. So according to our server, our client should be receiving each part of the audio stream with plenty of time to spare before it needs to be played. But clearly that's not happening because of the customer reports that we're getting. Okay, what about the client side? Yesterday, Guy talked about some really cool instrumentation that you can add to your client-side app. And this is especially useful if you're writing your client from scratch and you have access to some low-level native APIs. But let's say that this app that we're writing is browser-based, and we're just relying on standard HTML5 support for playing the media files. The best we could do is keep track of how long it takes the audio file to arrive and how big it is. But that's not telling us anything different than what we got from the server logs. So we're back to square one. Our customers are definitely having a bad time, but our logs can't tell us why. Both sides of the application insist that our average throughput is fast enough. Now, if you're a suspicious person like I am, you might guess that the problem is that word average. Yuck. No averages, right? That's exactly right. If we were looking at a metrics dashboard, we would never allow ourselves to look at something so gauche as an average. We want percentiles or a full histogram. And in this case, showing how the throughput of our connection changes over the course of the connection. To do that, we need to peer inside the connection in a way that's not easy to do with server or client-side application logging. So to crack this, we need another vantage point. Our client and server logs have the best intentions, but as we kind of expect, they're lying to us. We need to look past them and instead look at the network itself to see what our server really sent to the client and when, instead of what it thinks that it sent. Okay, so what do we want to capture from the network? Historically speaking, there have been two things that are relatively easy to collect. The first is called flow data, or net flow. And this is the traditional answer, partly because business-grade routers, business-grade, can collect this in hardware and will often provide it to you for free. So this is good. You don't have to worry as much about the collection side of this data source. You can just sort of tap into it directly and start seeing what you can see. That's good. Unfortunately, flow data isn't going to work for us in this particular example. Just like our client and server logs, it can't peer inside of the connection. It's going to be a summary of the behavior of the connection as a whole. So it's going to give us that same average throughput metric that we were already getting from our application level logging. So not very helpful. Instead, we're going to focus on packet captures, or PCAPs. These provide a wealth of information. You get to see the size and relative timing of every packet in a connection. And you can see whether and when individual packets arrive at the receiver. And you can see into the state machine that TCP uses to decide when and how quickly to send data across the wire. This is exactly what we want. This is the visibility that we need to capture the information that we need to debug and solve our problem. Now, one nice thing to point out is that we don't need to look at the payload of our connections, the actual HTTP requests and responses that are being sent. Instead, we just need to look at the packet headers that our transport protocols use. Now, that's useful because it gives us a better privacy story. We don't have to look at any potentially sensitive information in the network traffic. And it also means that we don't mind if the payload is encrypted, which obviously more and more of that is true these days. More and more sites are moving to HTTPS. Quick is encryption non-optional. So if you need to sort of do deep packet inspection looking at the content of the packets, more and more connections are going to be outside of your visibility. So the fact that we don't need to do that is a win. This is also useful because otherwise our packet captures would contain a lot of data. I mean, a lot of data. Every single byte that's sent on the wire. But if we only care about the transport headers, we can ignore most of that. Don't collect it in the first place. And that's great. That gives us a substantial savings in the amount of data that we have to store and analyze. Okay, so we're going to collect some packet captures, and we're going to test our hypothesis by looking at those PCAPs, both for the problematic connections, the one where we know that the customer is reporting this popping and audio dropping. And then we're also going to look at some of the PCAPs for non-problematic connections. And we're going to see if there are any interesting differences in the throughput characteristics of each. Okay, so let's look at a non-problematic connection first. So Julia, yesterday, mentioned Wireshark as a great way to dig into PCAPs that you've collected. And it's a great tool, and you should definitely be using it. So let's see. If we open up a PCAP in Wireshark, what do we see? I would argue that this is actually not very helpful. Wireshark is great. I'm not saying don't use it. But in this particular example, it's very dense, and it's not really giving us immediately useful, actionable information. And in particular, can you tell me what the throughput of this connection is, just looking at that table? Right? If you've got really good eyes, you can maybe squint at those numbers and tell me, right? Because, I mean, the data is there. You can see the size of each packet. You can see the relative timing of the packets. And so if you do the math, you can figure it out, right? And you can certainly write some code that sifts through that as well and calculates those. But for manual investigation, I would argue that this is not going to cut it. And instead, what we want is a visual representation of the connection. So this is a notation called tracegraph, which has been developed by my colleague at Google, Van Jacobson. And now, without having told you anything about how this visualization works, you can at least see that it's like a nice, pleasing line. There's not any kind of weird kinks in it or anything like that. So just sort of viscerally, you can see that this is a well-behaved connection. But let's go ahead and dig deeper. What does a tracegraph show? So the x-axis is a measure of time. So it's usually the number of milliseconds or seconds since the start of the connection. And the y-axis is the number of bytes. Okay. So what's nice about this is that if you divide bytes by time, you get a bandwidth number. And so the slope of this graph is the throughput that you're achieving with your connection. So we can see not only that this connection is nice and steady, it's an evenly, an even line here without a very much change in derivative or anything like that. But we can also run the math and we can see that in particular it's holding steady at just under about 4 megabits per second. Pretty good. Okay, now what else can we see? Let's go ahead and zoom in this lower section of the graph here. So it's the very beginning of the connection. We're going to get to see if the behavior is any different as the connection is ramping up. Okay, so here we've zoomed in a bit, and we can see that at the beginning of the connection, it's not as well behaved as we thought. Now, we can also see now that we're zoomed in a little bit more that there's actually multiple lines on this graph. It's not just a single graph of the data in the connection. Okay, so in particular, we've got this green line, and apologies if the colors are a little bit washed out. I'll try to highlight it with the pointer as well. We have the green line, which is the sent line. So this is the data that the sender is trying to inject into the connection. And then the blue line is the acknowledged line, or the ACK line. And this is a measure of how much of that data and how quickly is arriving at the receiver. And now those are definitely going to be different. The entire point of TCP is to detect when there are differences between what the sender wants to do and what the receiver can accomplish, and to do the right thing in response to that. So it's completely expected that these lines are different and they have different shapes and gaps between them. And what's going to be interesting is looking for particular patterns in how they're different. Okay. We also have this yellow line here, which is the receive window. I'm not really going to talk about the receive window. If you know more about the particulars of TCP, we can graph it, but we're not really going to talk about it for the rest of this talk. Okay. Now we can also see that there are retransmits. So this place here where the green line is sort of moving up nicely, and then it jumps right back down. This is where the sender had to retransmit some data. So remember, the y-axis is the bytes in the sort of life of the connection. So if we see a particular y value appear in the graph multiple times, that means that the sender tried to send that byte multiple times. And so that's why this is an indication of retransmission. And you can see it very visually. There's a severe drop down in the sending line of the graph. And we do also highlight that with these red circles as well, just to really call it out, because those are often going to be sort of important points where you need to investigate what's going wrong. Okay, so now let's zoom in on some of those retransmits. So now we've zoomed in far enough that we're actually seeing individual packets. So we've got the individual sent packets here, and again, with the outline, the colors might be even harder to see, but in general, the one to the left will always be the sent data, and the one to the right will always be the received data, because otherwise you've got some weird non-causality thing going on. So we can see the individual packets being sent by the sender. We can see the individual acknowledgement packets coming back from the receiver. And when we do have retransmissions, we can see the individual packets that were being retransmitted. So that's great. We can zoom in pretty closely here. And we can also see this blue shaded region up here is what's called a cumulative ACK. So that's when a single acknowledgement packet comes back from the receiver, and it's acknowledging multiple sent packets from the sender. This usually happens because of a dropped packet or out of order packet arrival, but it doesn't have to be that. Okay, great. So we're seeing a lot of things here, and from this we can see that the sender is trying to send data faster than the client can receive it. And eventually the sender infers enough information about what the client can support, and it ramps down and it eases back. And we end up with a steady state behavior where the sender is sending data at the same rate at which the receiver can receive it. Right? This is exactly what the beginning of a TCP connection is trying to do. And we can see visually into how that process works. Okay, so let's zoom back out again. Ignoring the beginning of the connection where we have that sort of detect what the client can support behavior, we've got a nice steady state where the TCP machinery is humming along nicely. If we were to measure the overall slope of this graph, right, so just take the total number of bytes, divide by the total number of time, we would get the average throughput, exactly the same number that we would have gotten from our server logs and our client logs. And that's great. We can use this just sort of as a validation step that what we're seeing in the two different data sources lines up and is consistent with each other. Okay, so now the story is different if we see a connection whose throughput changes over time throughout the course of the connection. Now this is not one of those misbehaving connections that's causing the audio popping. This is just sort of a still smooth connection in the sense that TCP is humming along nicely and responding to changing network conditions. But those are real network changing conditions, right? We're seeing different throughputs because the network is actually supporting different values at different points in the connection. So we can see here at the beginning, we're getting about 75 kilobits per second, but then something causes it to ramp up. But maybe we're not congested as much. Maybe we're not sharing the link with the wife who's watching Netflix at the same time that I'm watching something on YouTube, as an example, right? So then the throughput that I can achieve starts to ramp up, and eventually at the end of the connection, we're getting more like 800 kilobits per second or so. So again, this is possibly when we're seeing differences in these graphs, it's not necessarily that there's anomalous behavior or misbehaving connections. It could just be that we're seeing into what the network is actually doing. Okay, so now that we've got this new tracegraph tool, let's actually take a look at one of those problematic connections. This here is zoomed in on just a portion of a connection that's misbehaving so that we can see some of the details better. And this does not look very happy, hopefully. Again, we haven't been looking at trace graphs for very long, but this is not a nice smooth line. It's not steady over time. There's clearly something going on here. The sent line is skipping all over the place. It's trying to send pretty quickly, and then there are these flat parts here where it can't send anything at all. There's places where it jumps back down and has to retransmit. And the flat parts here are going to be especially problematic when we dig into this a little bit more. But what is it that we're seeing here? This is an example of something called buffer bloat. And I really like this frog. I think he's a good spirit animal for network problems like this. Buffer bloat is a pretty insidious problem, which we've known about for a while. But we've only really started paying attention to it in the last 10 years or so. But what is it? So let's go back to the trace graph. What can we see about the throughput here? So as I already mentioned, the slopes of the sent line and acknowledgement lines are different, right? So here we're trying to send, the sender is trying to send around 102 megabits per second. This is clearly not the exactly a packet capture from this example application, because I didn't write that example application. So the 102 megabits doesn't line up with the numbers I was quoting earlier. But the sender is trying to send really, really quite quickly, and the receiver can only keep up with about 25 megabits per second. So the sender's sending a good 4 times as quickly as the receiver can keep up with. Okay, so it's not just, though, that the slopes are different, because that's what we saw in the well-behaved example as well. That was just an example of TCP ramping up and figuring out what the client could support, and then taking that into account and being a good citizen and only sending at that rate. But if we were to zoom out from this connection, we would actually see that TCP is never recovering. We're always seeing this spurty behavior where we've got too fast of a rate, and then eventually things collapse somehow, either with retransmissions or with gaps. And then after a bit of time, it recovers, and we try to start sending again, but at the same too quick rate that ideally we would have detected and gotten around. Okay, so that's not good, right? The spurtiness isn't just ugly. And these flat periods here are the smoking gun for that behavior that the customer is seeing, right? So overall, on average, we're achieving a throughput that should be able to support the application use case that we care about. But what's actually happening is there's these large gaps here. So the client receives some amount of audio data, starts to play it, and then the connection drops out. And by the time the sender starts sending more data, the client has run out of audio to play. And so they have to stop. And so yes, on average, we can maybe sustain the rate that we care about, but it's not the average that we want. We want to look at these histograms, just like we talked about. And so these flat parts here are especially bad. Okay, so this is great, right? We've figured out what's going on. We've solved our problem. Well, not really. We've explained the behavior, but we haven't fixed it. So how do we do that? One option is that we could have our client buffer the audio data that's coming in and wait a little bit longer to start playing, right? And what that's really going to do is it's going to mean that there's more wiggle room, right? We're not going to solve the network conditions. We're not going to fix them. We're just going to try to mitigate them when they happen. So if we have a large enough buffer, then we can continue to play the audio while we wait for the client to the connection to start back up. And the hope is that our buffer is long enough that we can sort of get over any kind of gaps that we do to discover. Now that might seem like a hack, and it's probably not the best user experience, right? They're going to ask for a song, and we're going to say, oh, I'll start playing that song for you in about 30 seconds so that I can hopefully get around any network conditions that happen. That wouldn't be the best. I will say it's at least a hack that's informed by data, right? We can set that buffering value to actually be in line with the network conditions that we see for real customer traffic. So not ideal, but in some cases it might be the best that we can do. Is there a better way? What's causing the buffer bloat? And can we get rid of it? If so, then we wouldn't have these outrageous gaps that we have to smooth over. So this is a nice segue into another one of the performance metrics that you can see visually in a trace graph, and that's called latency, which is a measure of how responsive a connection is. So not how much data can you send and how quickly, but a raw measure of how long does it take any individual piece of data to arrive. And the specific thing that we usually measure is called the round trip time. How long it takes for an individual packet to make it from the sender to the receiver, and then how long it takes for the acknowledgement from the receiver to make it back to the sender. So round trip because it has to go both directions on the wire. And we can see the latency of a connection, the round trip time of a connection in a trace graph, just by looking at the horizontal distance between the sending line and the acknowledgement line. And that's telling us for an individual packet, or a byte of data in that packet, how long did it take for that byte to be acknowledged by the receiver? Okay, so for this buffer bloat connection, what's interesting is that we're seeing very, very different latencies at the beginning of each, I'll call it spurt, than at the end. The latency grows sort of as the data is being sent along the connection. And what's happening? This is the smoking gun that tells you that this is a buffer bloat problem and not some other kind of performance issue. Very, very briefly, the problem is that there are some routers in between the sender and the receiver on the internet. And those are very deep in the bowels of the internet inside of ISPs that we have no control over, and we have no control over how they're configured and what they do and how they're linked together. But we do rely on them for our data to make it from the server to the client. Now the problem is that some of those routers have buffers in them, and the buffers are too large, hence the name buffer bloat. So now when the server is sending data too fast, TCP relies on some kind of feedback mechanism from the client. Basically a signal saying, whoa dude, back off. And if we can detect that signal on the server side, the server is well behaved and nice and gentlemanly, and so it backs off and slows down to a rate that is sustainable. And the problem is that these large intermediary buffers out in the internet get in the way of that signal making it from the client to the server. There's interesting technical details in how exactly it gets in the way, but the take-home message here is that the sender can't detect the signals that the client is trying to send, saying, I can't keep up, back off please. And that's what causes the sending rate never to tamp back down, and eventually the ability or the inability of the client to keep up becomes catastrophic. Right? It's not just that like we're dealing with packets being dropped every now and then. It's that we actually get into one of these failure cases where we're not sending any data at all, or where we have to start resending data a lot. Okay, now the ideal solution here would be to get those intermediate routers to shorten their buffers. But again, we don't have control over those routers, so we can't make that kind of a change. That's not really an option. Now, if you're running a fairly recent Linux kernel on your server, you can activate what's called BBR, which is a new congestion control protocol that some of my colleagues at Google have developed. They published it in a paper, and they've committed it upstream to the Linux kernel, so it's available now for use. There's not nearly enough time to get into how it works, but the short version is that they use a better, hey, please back off signal from the client, one which is more able to make it through those large intermediary buffers. And then the server can detect that signal and ramp down its sending rate, everything's hunky-dory. And it works in the presence of those janky routers that we don't have any control over, which is really the key there. So all is not lost, kind of. We have a solution if you have control over what kernel you're running. If not, there's various sort of application level things that you can do to mitigate. I won't try to claim that we've solved everything here with happy unicorns, but we've at least got some data that we can work with to tell a good story about what happened and what we can try to do to react. Okay, so what have we been doing with all of this? We've been looking for interesting patterns in these PCAPs. And ideally, we were able to do some of that visually, which is nice, because as humans, we're much more visual people, so that's better for our pattern detection. But we really haven't talked about how to get those PCAPs in the first place, right? I sort of started with, hey, I've got a PCAP, let's open it up and see what happens. But how are you going to get them in the first place? So let's start collecting some packets. We've got these huge stream of packets going in and out of our servers. How are we going to capture them? So a good first step is to just run TCP dump on your servers. Try running it a few times manually to get a handle on what a PCAP file looks like. And I'm going to sort of defer here to Julia, because she gave a really good overview of that yesterday, and she's got a great zine that you can download that goes into more detail. So definitely check it out. Now, in her example yesterday, she used TCP dump as a one-off, right? She was responding to a particular problem, so she logged into the server and started running TCP dump with a very particular filter expression because she knew which packets she was looking for. And she saved those and looked at them and answered the problem. And then, importantly, she turned TCP dump off when she was done investigating this problem. Okay? We want to do the same thing, but in a continuous, long-running way. We don't know in advance which packets we'll need to look at. And we don't want to turn off the packet collection until we turn the servers off themselves. Okay? The good news is that you can still do this with TCP dump. Instead of starting it manually, just let your existing job control system make sure that a TCP dump process is always running on each server. Right? You've already got something, presumably, which is making sure that the server application itself is running there. You're not logging in and manually starting that. So use the same mechanism just to make sure that TCP dump is running. TCP dump includes options for rotating its output files in a number of ways. So if you use one of those, your long-running TCP dump process will end up creating a big pile of PCAP files in a directory of your choice on the server, on each of your servers. Okay, so now you need to ship those files to some other location first so that you can analyze them in a single centralized place. But more importantly, so that you don't fill up the disk on your servers, right? We're writing lots of big files, we've got to get them away somehow. So again, let's not go crazy. If you don't already have some kind of dedicated file shipping service to draw on, just use rsync and a cron job, right? It doesn't need to be rocket science. This is a great start, and it doesn't rely on any tools that aren't readily available in your favorite Linux distribution's package manager. So it's great. Okay, but you might need more control over your packet collection, in which case you should switch to libpcap. This is the C library that TCP dump is using under the covers to actually tap into the stream of packets flowing through the kernel. It's not that bad of an API to program against, and you can find bindings for it in pretty much any higher level language that you might want to choose from. So this is not saying that you have to start writing anything in low level C or anything like that. So writing your own packet capture program opens up some interesting possibilities. You can create a more complex filter than you could get from TCP dump's filter expression language. So for instance, Google, as you might expect, has a lot of traffic flowing across the edge of its network, all of the cat videos that anyone's watching on YouTube in particular. And so we need to sample our PCAPs somehow. We can't collect everything about every single connection. There's just too many of them. So what we do is we use a flow sampling filter where we don't collect information about every connection. We only collect information about some of them, a statistically sampled subset of them. But importantly, for every single connection that we collect, we want every single packet in that connection. So we need to have something about the connection itself be part of our sampling logic. Now that is something that you could write as a filter expression for TCP dump, but it's going to be hairy and ugly, and it's not going to be fun to write by hand. So you could do it in code instead. You can also have your filter expression change over time. So one of the things that we're doing in our stack is that we are biasing our sampling to target customer populations that we think are, or that we suspect are having issues. So sort of like we're sort of collecting nice and evenly, and as particular client populations start to give us signals that problems might be occurring, we shift it so that we collect more packets from those instead of from other client populations as a way of trying to verify that sort of suspected outage that we're seeing. And that's something that you can only easily vary over time if you have a more programmatic interface with your packet collection. And lastly, it means that you can make this more real time. So with a custom collection program, you don't have to write the packets into a file and then rely on something like rsync to send them back to an analysis server. So at Google, for instance, we have a nice, well-supported company-wide RPC system. And so our packet collection daemon can just inject the packets directly into that and send it back to our analysis servers without ever having to write it to disk first. So that's good because we're saving some disk on the server side, which, that's a non-trivial win. But it also means that if we do a small amount of the analysis at the collection point instead of back at that centralized location, we can get a really useful signal about certain bits of high priority outages within seconds. Right? We're doing it immediately as soon as we see the packet that exhibits the behavior, and we're sending a signal about that back to the rest of our monitoring stack right away. So you can definitely do something with libpcap that's pretty cool. Okay, great. So at this point, we have a good story for capturing packets from our servers, and we have some interesting patterns that we can look for in those PCAPs. But you'll notice that this was a pretty manual process. Whether we were using Wireshark or Tracegraph, we were only looking at a single connection at a time. And we don't want to throw that away, right? That's definitely useful when you need to do manual debugging. But we also want to turn this into something more automated, requiring less human intervention. So with this audience, I can safely assume, hopefully, that you have a decent story for that, for automating your monitoring story based on signals coming in from all of these data sources. Or at least that you know that you need a good story for that, and you're actively working towards making it happen. So what's nice about these packet captures is that with care, they're not really different than any of the other data sources that you might want to tap into. So what do I mean by with care? Well, we're not injecting the packet captures themselves into your ELK stack. What we're passing into that is the results of this analysis process. So you end up with something that looks like a JSON blob, right? You've got the timing information about the connection, you've got some aggregated or anonymized information about the client and server side, and then importantly, you've got the results of your packet analysis. Did this connection exhibit buffer bloat or black holing? What was the throughput that it achieved? Okay, so we're done. I'm being signaled that we're running out of time, so take-home messages. Packet captures are useful. You can find useful information in them that you can't get from other data sources, I would claim. But in order to leverage that information, you don't need to make any outrageously large fundamental changes to your monitoring stack. This is just another data source. Okay, and with that, thanks very much.